So I want to sort of summarize today something. So originally I come from high energy physics, so a completely different field, but I've gotten very interested in black holes since basically all of my postdoc time, 4 or 5 years. And so I want to summarize work that I've been doing with various groups of people over the last 3 years, which I think starts to approach a point where a summary is useful, which is about making numerical relativity work, but not just in GR, which I guess most of you work on, but in modified theories of gravity, by which I really mean modifying the gravitational content of the theory, not just adding matter fields, for sure, not just minimally coupled matter fields, but changing really the gravitational equations. I won't get into why we should do that or whether we should do that. I'll approach this from a perspective of we have observations now, and I think they are very exciting. Actually, not just gravitational waves, but today I'll talk about gravitational waves. So I think we should make use of them as much as we can. So we should probe for modifications. That'll be my perspective. And that's also why I'll talk most of this talk about effective field theories, which I think are a very nice framework to do that systematically. And I'll give a brief overview of that in the beginning. But you can, the technical part of the talk, you can really understand. It's unimportant for whether you are viewing effective field theories as the meaningful framework or not. Okay, before I jump in, since there's quite a mixed bag of concepts and I'm summarizing quite a lot, I try to sort of find the sweet spot between being sufficiently technical and not too technical. If there's either side, please just interrupt me. I'm happy to skip slides in the end. So what I want to ideally get through today is the 3 parts. So I want to first say a little bit about what I mean by gravitational effective field theories. And then you are probably familiar with well-posedness in general relativity. I want to summarize recent work with Paul Figueras and Aaron Kovacs, which is also based on other papers previously, which sort of makes it work that in such effective field theories, we can find the well-posed initial value problems. And then finally, I'll talk a little bit about implementation, which is actually something that I've worked on for the second part, and which has sort of inspired at least my contribution to that well-posedness proof, which is about the nonlinear evolution in the leading corrections that you get. And there's a star from the leading corrections, which is why I have the part 1, which relates to field redefinitions. And then you might be worried about ghost instabilities, because I will talk about modifications which include higher derivatives. And so these are known to come with so-called Ostrogradsky ghosts. I'll briefly say something about that now in the very beginning, but then I'll keep all of that under the hood. All right, so let me get this out of the way. I think all that it matters for the talk today is that these Ostrogradsky ghosts are not an obstruction to well-posedness. And there's a quite obvious argument to me that one can make. So the usual way of understanding these ghosts is that if you put a Hamiltonian and you have that, if you put a Lagrangian and that Lagrangian has higher derivatives, and you find the equivalent Hamiltonian with the prescription that Ostrogradsky gave almost more than 150 years ago, then you find a Hamiltonian which is both unbounded from above, as usual Hamiltonian, and unbounded from below, which is typically understood to cause an instability and can also cause an instability. It doesn't need to, but it can. And that's sort of what the instability is typically understood by. But equivalently, you can recast the original Lagrangian into a second order Hamiltonian, second order Lagrangian, which is sometimes referred to as the Helmholtz, that's L missing Lagrangian, which is a Lagrangian for more fields than your original Lagrangian, but all of the fields are second order. That is always possible. And then the equivalent statement of that it's always unbounded from above or below the Hamiltonian is that the fields come with opposite sign kinetic terms. And so I'll understand that as a ghost. And here's a simple example of 2 scalar fields. And if I adjust this sigma here, if I put it +1, I have no ghosts. And if I put it -1, I have a ghost. Which of the fields is a ghost is your choice. depends on what you define as your physical energy. So that's what I'll consider as a ghost. So I'll consider that as opposite sign kinetic terms. That's the generic structure. And if you really want to go through a Hamiltonian construction of a higher derivative theory, it can happen that you have first derivatives potential, but only first derivative. So if you derive the equations of motion or the field equations of this Lagrangian, they look like this. And they are really just wave equations. And on the right-hand side, you have potential. And so from this, it's very obvious that the potential ghost instability, right? Because it's just the question of whether this sigma has its +1 or -1, is purely in the potential terms. It's not in the highest derivative parts of the equation of motion. And so by that argument, it cannot affect the well-posedness or cannot affect the principal part of the field equations. And so really the two concepts of Ostrogradsky ghosts or potential instabilities, physical instabilities, and local well-posedness are completely unrelated. All right, so I hope that with that, sort of, you're not too offended if I have higher derivative terms floating around. And I'm also propagating the respective. All right. With that, let me proceed to gravitational effective field theories, and you'll see the higher derivatives appearing immediately. So the effective field theory framework is very nice because it sort of captures a general way of just parameterizing all possible deviations that you can have beyond your low energy. And there's a bunch of assumptions that you make, and that's that you fix your light field content. And that can be the metric, and it can be other degrees of freedom of the metric than the metric. But think of it as, for now, just as being the metric. And then you fix your symmetries. I will not break the symmetries. I'll remain with Lorentz invariance fully intact. And then finally, you have to define some expansion scheme by which you order your higher order interactions. And that can be actually a derivative expansion or a curvature expansion. And typically, it's just a mixed expansion of derivatives and curvature. I actually think that it would be very useful in the future to disentangle derivatives and curvature. But for now, the community just basically goes by dimensionality in some natural unit scale. And therefore, it's a mixed expansion of derivatives and curvature. And then that expansion defines a scale, right? And if your new physics is heavy with respect to that scale, then it's effectively integrated out, and its physics is captured by the coefficients in that expansion. So within the regime of validity of your effective theory, which just means that your higher order corrections are small compared to lower order, the effect of any unknown, people call it UV physics, because it comes from high energy physics, ultraviolet physics, is captured by the coefficients in that expansion. And so it's a nice framework in that sense, because I can now say I fix my infrared field content, and then it introduces rules to how I should think about testing modifiers. And you might have seen this zoo of modifications that you can write down. I think this sort of gives a nice way of sort of understanding what is possible. That's all right. And so if you do that for gravity, then you start actually with the cosmological constant, but I will not talk about cosmological constant. And then the next term is just the Einstein term, just the Ricci scalar, and some arbitrary scale, which I've chosen here to be the Planck mass. And then the next terms are the ones which are quadratic in curvature. And you could also think about covariant derivatives, but you can show by these reductions, which are specifically, you apply all the possible index symmetries that GR has, or that diffeomorphism invariance implies. You use all the geometric identities, and you use I'm specifying to 4 dimensions, which in particular means I can use the so-called Gauss-Bonnet identity, which relates the Riemann tensor squared to these quantities up to boundary terms. And so with that 4D specific identity, you can remove that term, and then these are the only two terms that you have at the second order. And then you can go on to the cubic order, and you have 8 terms. It starts to become more and more ugly. And actually, that's like generically, when treating general relativity as such an expansion, the complexity is really diverges pretty crazily. So it's 8 terms at cubic order, and then I'm not even writing down all terms at the quartic order. And so that sort of would be the leading part of that expansion. And I think if we were able to do all of that, we would really capture all the corrections to vacuum general relativity. And this is the complexity before using field definitions. And so field definitions are an additional simplifying step. And I think it's fair to say that if your evolution and the way that you look at physics remains perturbatively close to the GR manifold, then the field definitions are justified. I think with all other physics at the boundary or wherever, it's a little subtle whether the field definitions are something that should just blindly use or not. But in any case, if you use the field definitions, you can, for instance, transform the metric like this. You can take the metric and transform it, well, to the metric plus additional pieces, where x can be any scalar and xab can be any tensor, right? Because it has the same index structure as the metric. And you can think of x and xab, I can choose them to be combinations of the Ricci scalar. And by that, I can order by order remove actually all the terms which have a Ricci scalar or tensor. And therefore, I'm of course picking up corrections then at the next order. But since I'm using a systematic expansion, I can push them always to the next order, which I'm then neglecting in the expansion. And by that, you get rid of all these terms. That really simplifies the expansion. And that means that you would then sort of think that corrections to vacuum general relativity occur at cubic order first and then at quartic order. All right, if you do not, then the leading corrections occur at quadratic order. So if I can now perform these field definitions, I can just as well only remove part of these terms by field definitions and keep these terms. And you will see in the next part of the talk that these terms are the ones which are going to help with well-posedness. And the reason is pretty simple to understand, because these are the terms which have the highest number of derivatives acting on a single metric. So here, the box acts on top of the derivatives inside the Ricci tensor on the single metric. So it's up to 4 derivatives of a single metric. While in here, there's only 2 derivatives of a single metric, and so on in all other terms. And the same. And since the highest number of derivatives is what dominates the principal part, those are terms which affect the principal part most, and keeping them helps.
In doing this, are we restricted to parity preservable theories?
Up here in the slide, yes. And you would, I guess you're right, yes. So there's a term, so here the while tensor has a dual, which you can denote by a while star, and then you would have a while dual while interaction, which would be parity breaking. But all of what I'm going to, I haven't written down these terms here, but all of what I'm going to say will also work for the parity breaking.
Yeah, one question. So if you're treating this as an expansion where the corrections from higher order terms have to be perturbative, can you not do an order reduction of the equations where you use the 0 order equations to relate higher to lower derivatives, and then you use this relation to reduce the order overall?
I mean, so first of all, of course, you can do that. Like technically, you can do that, and then the equations are immediately well posed. It's a slightly different statement that the action has a perturbative expansion, or that locally at each point in the time evolution, you can perform a perturbative expansion. And I mean, people have tried that, and maybe Vito has been involved in that. As Vito has been involved with almost everything. But people have tried that, and what you see if you compare to explicit time evolution without performing that simplification step, is that you pick up sort of so-called secular effects which build up over time, which sort of take you away from the actual solution. More than you would, and even in a perturbative regime, than without.
So in the orange boxes, you have the terms that you have to consider. They cannot without the that.
Even with field derivatives, yes.
The final box, that's the term you want to consider, but in principle you can.
Precisely. So the pink ones, they will help me with well-posedness, and I will reintroduce them with another set of field definitions to make the well-posedness work. So if you use that version of the theory, you can really try hard. I haven't succeeded, and no one has succeeded in writing down a well-posedness. All right, more questions. Good. So then let me proceed with well-posedness. So as I said, this is work which was finished this year with Figueras and Aaron Kovac. And it's actually based on previous work, which is from the 80s, and it's something that I find amazing that this paper doesn't receive more attention. It's a paper by David Noakes, who was a student of Bob Wald, and he has, in this quadratic truncation, he has shown that it's absolutely well-posed just as is GR, even already. And then it's sort of it got completely lost. And that paper is actually what motivated me to work on numerical relativity in the first place. So what I want to take you through is, I want to talk about general relativity first, and you probably know about well-posedness in general relativity, but it will help to introduce the concept of Lie weights, which I will then be able to sort of fit nicely the preceding parts. I will summarize the story in quadratic gravity, which is, again, this work by David Noakes. And then I'll go to the cubic, quad, and actually all orders in the effective. All right. So well-posedness, what we mean is that if you want to set up an initial value problem, meaning that we slice our space-time into spatial slices and time direction, we put initial data on the spatial slice. Then we want that the propagation of that initial data exists. In general, if you consider global well-posedness, we want it to exist for all future time. But I would be happy with local well-posedness so that it persists for some future time. We want it to be unique, and we want it to depend continuously on the initial data. And that's sort of the physical way of phrasing well-posedness, but it's also very close to the mathematical definition. As you know, well-posedness has been proven for general relativity already in the 50s by Yvonne Choquet-Pouha, whom I recently tried to meet. She's still alive, amazingly, because I think it's a very sort of groundbreaking work, and she lives actually close to Paris. So she had her 100th birthday recently, and some birthday celebration for her. Sadly, she didn't appear. I think she's very old. Of course, it took then the development of a lot of numerical techniques and also just the development of supercomputers to be able to perform these simulations, but the mathematical well-posedness is very old, and therefore Noakes was also able to generalize that in the 80s to the quadratic gravity theory, which we are only starting to simulate now. And then now we can try to move towards. Okay, so let me introduce the concept of Lie weights. So this is not the way that you would understand well-posedness in modern mathematical language, but I think it's easier to understand than the modern. So because the modern way of understanding it works with the first order equations, and then looks at the characteristic polynomial in the end of the equations, of the principal part of the equations. So here we are going to label second order equations. We're going to label them by an index I, and we will insist on having the same number of variables so that the equation has a reasonable chance of having a solution. And then we focus on the principal part, which means the part with the highest derivatives. And then the statement is that that can be diagonalized if certain conditions can be met on that system of equations. And these conditions relate to finding positive integers, sets of positive integers, which are labeled Si and Ti, such that these two conditions hold, which basically the first one tells you about this, the highest derivative structure of a variable in its own equation of motion. And the second one tells you about the contribution of the other variables to that equation. I think it's nice to sort of go through that mathematical definition if you have enough time, but in the talk, it's much better to sort of give an example, and I'll do so on the next slide. But this gives basically a prescription to diagonalize the principal part of equations of motion if it's possible. And if these conditions are not met, you cannot diagonalize the principal part. And so what's nice about this is that if you can diagonalize the principal part, then there are generic math theorems which tell you that in a suitable gauge and everything, there exists a well-posed initial value formulation. And of course, that also depends on certain conditions on the initial data. But that is really the question, whether we can diagonalize the principal part is the key issue that we have to face in the higher derivative. So here's a simple example. It's the simplest example that I think of when preparing these slides. It's just two wave equations, but then I give one of the wave equations a second order derivative time. So it's not obviously diagonal because there are more than, doesn't just depend on second derivatives in V, but it also depends on second derivatives in U. So now you can formally think of these indices and try to fulfill the conditions of the previous slide. And I can explicitly take you through that now. So the equal indices, so either 1 or 2, they refer to the highest, to the highest derivatives of the variable itself. So in the first equation, it's the variable u, and the second equation, it's the variable v. So in the first equation, I picked the indices 2 and 1. So 2 minus 0 is 2, which is the order of the equation in U. And 3 minus 1 is also 2, which is the order of the equation in V. And now I've picked one higher in the second variable, such that also the other condition is fulfilled, namely 2 minus 1 is 1, which is larger than the derivative of V in the first equation. And 3 minus 0 is 3, which is also larger than 2, which is the order of the derivatives of the other variable in the second equation. So it's useful to sort of put these, integers up, or I find it useful to put the integers above the equations, and it's easier to remember them. I'll keep doing that for the rest. Then I don't need to like add a long list of integers. Which one goes to strike? So these integers tell you how to diagonalize the equations because the second set of integers is one higher than the first. So you'll have to differentiate the second equation. And you can introduce an additional variable, which I call dot. Note that I really mean a new variable here, not just a physical dot. And then the first equation becomes a box of dot, picks up one more derivative on the right-hand side, but that doesn't matter for the principal part. And the second equation now reduces one order on the right-hand side. Now the principal part is diagonal. And that's possible because, or it's related to the fact that I can find such Lie. All right, so and then in this simple example, the system can be diagonal. Okay, so now getting more complicated, gravity. And I will typically now give an integer to a whole set of equations respective to one field, by which I mean that of course, there's still multiple equations for space-time dimensions, but in that equation, the structure is diagonal anyways. So I don't need to worry about, I can sort of have super indices for those. In any case, so for general relativity, you probably heard the story. You can define a gauge potential, and then really the equation of motion or the field equations are just the Ricci tensor equals 0 in vacuum general relativity. And the Ricci tensor, this should actually be flat D'Alembert. And then there are other corrections. These are corrections which are only first order inverse derivatives. And if you pick a gauge potential, which is either 0 or constant, then these ones here vanish as well. And then the system is already diagonal. So in a suitable gauge, the vacuum Einstein equations have already wave-like form. They are diagonal by this sort of 4, and then you can use the theorems that actually Choquet-Bouhard used in her. So now we go to sort of the next order in the effective field theory. We go to quadratic gravity. So to quadratic orders in curvature. Here it's useful to use the Gauss-Bonnet identity. On the previous slide, I had the version with the Ricci tensor. It's useful to use the Gauss-Bonnet identity and instead write the Weil tensor squared, because then I can identify the masses of the additional modes already at the level of the Lagrangian. So this actually is very close to the Helmholtz Lagrangian, which I talked about previously for this type of theory. And so now you have the masses, you have one additional scalar field and one additional tensor field, both are massive, and these are the two masses. This one is a ghost. Okay, so if I take this field, then you can write down equations of motion. And of course, if you vary this equation of motion, you first get fourth order equations of motion. And it's useful to then not diagonalize them, to reduce them to second order by introducing fiducial variables. And I've done that here already. And this is something that was done at the linear level by Kelly Steller, who sort of started looking at these theories in the context of quantizing gravity. And David Noakes sort of picked up the linearized prescription and generalized it to the nonlinear theory, understanding that also the nonlinear theory propagates these respective additional degrees of freedom. And it's very helpful. Now I can identify, I propagate the metric, which is just the massless spin-to graviton, where there's a whole sort of story about gauge dependence. And if I want to count the numbers of initial data which match to a massless spin-to field, it's a complicated story, and I have to remove gauge constraints and so on and so on. This whole gauge difficulty doesn't affect the other equations, where you can really go through the counting of the respective tensors, and you can understand that this equation corresponds to a massive spin-0 scalar. It has 2 pieces of initial data, and this one corresponds to a massive spin-to field. It has 10 pieces of initial data, which are 5 degrees. So these are the equations in second order form. And now I can start to think about whether they are diagonal or not. And you can see that if I remove this term, which I can by picking the masses equal, well, then there's really nothing on the right-hand side which has second order derivatives. So then it's already in wave-like form. If I do not do that, well, then I have to work harder and I have to give these Leray weights. But I can pick Leray weights which are one order higher of the last equation, and that's exactly what Noakes realized in his work. And then he explicitly goes through the diagonalization to make the proof form. So even for unequal masses, you can find these Leray weights such that you can diagonalize the system by taking additional. So it admits second order field equations which have the appropriate Leray weights to be able to diagonalize the system. And so by that, you know that the system admits a well-posed initial value. like actually formulating the evolution equations in a way such that you can then put them on a computer is a little bit of more work. But I'll not get into that. Okay, so now for the cubic case, the whole story sort of proceeds down a tower of additional massive modes. Now I've entered, so on the previous case, you had no box in the terms with two curvatures. Now you have one box, and you will see in the quartic one, you will have two, and you will have three, and so on. So if I have one box, you will now have sixth order equations of motion. And so you kind of already can anticipate that you will get another layer of additional degrees of freedom. And that's exactly what happens. If you sort of reduce the equations of motion to second order, then you can show that they take this form, where there's an additional layer, and I have the Weil tensor, because now I have, for the first time, the Weil tensor can be involved in writing down these all possible invariants. So now I will either have to propagate or remove the propagation of the Weil tensor. But really, you can see from the Bianchi identities that these Weil equations, they are not additional degrees of freedom. You can always use appropriate Bianchi identities to remove the respective initial data. So the only new additional degrees of freedom come from the Ricci variables, or of course you could change some of the Ricci variables for Weil variables if you wanted to, but it's not independent. Here I choose to sort of put all of that into the Ricci. And then there's one layer, as you had before, of a massive scalar and a massive tensor, and then another layer of a massive scalar and a massive tensor. And actually, this is very similar to just a scalar field theory, where you would add higher order box operators, and you would produce always kinetic terms with opposite sign down a tower of terms. Okay, if I have done that, it basically has the exact same structure as the quadratic gravity already, but now you have to remove this term from well-posedness. So you have to choose the highest modes to have the same mass, because that will get rid of this term. And then 4 equal masses, which in these coefficients here means this relation, this term vanishes. And then you can give Leray weights, which sort of proceed again down a tower of the equations, and you can again show that the system can be dynamic. And that, in this language of Leray weights, is the reason why you can find an initial value problem, which is well posed for such equations. So it admits a wave-like second order field equations, and then you can go on. And I'm doing it here now inductively up to order k in some order of these box operators. So then you have a tower, and I'm putting all the in-betweens here in this order k. You can give the tower of Leray indices, and you can again verify that the conditions are met. And the crucial bit is now, or at least the crucial bit for the effective field theory, is that this is not changed, and this makes sense, if you add terms with less derivatives of a single field to the action. So in the paper, we call these terms the regularizing terms, because they enable to write down a well-posed initial value problem. And then it doesn't matter whether the EFT also has other terms. That doesn't matter anymore for the well-posed applications.
Okay. So this includes all the terms that you showed previously.
Yes.
Okay.
So at each order of the effective field theory, you can, if you trust the field redefinitions, perform suitable field redefinitions so that you keep these regularizing terms, and then the respective initial value problem will be well-posed.
But this is only if you pick the degrees of freedom to have finely tuned mass.
So yeah, the highest, so there's a tower of massive modes, and the highest ones have to have the same mass. And you can think of, so, but of course, if you do use the field definitions, you can just pick them to be such that the coefficients of the highest ones happen to have that structure. Even if you do not want to do the field definitions, I think you can just take terms from the order in the effective field theory that you truncated. You just take the next order terms and you pick out the ones which give you the respective box structure, and you pick those coefficients to have the equivalent masses. And then these are higher order in your EFT. So by the whole sort of approach of EFT, you expect them to be irrelevant for your problem. Okay. So I think the crucial question that remains in whether this is useful or not is the ghosts. And the crucial question is that if you make the ghosts sufficiently heavy, then you will not run into the instability. And you will see some evidence for that in the quadratic theory in a bit. And I think there are generic arguments, and I'm currently working on simple scalar field examples to sort of clarify these generic arguments, that this decoupling will always happen. And then it's a question of whether you can sort of find the sweet spot at which you do not completely remove these degrees of freedom to capture the higher order effects, but you also don't run into the ghost. All right, but again, this admits second order field equations and therefore has a well-posed initial. All right. So this means that I can go back to this slide. GR has a well-posed initial value problem, and now all these higher order towers have as well. So again, we haven't tested that on a computer, and what I want to do in the remainder is I want to show you how we are starting to simulate this second order, which notice you can remove by field definitions. And so, I mean, there's a simple actual reason for why I can show you this work and not yet this work, is that, well, I've started working on this because we found the Noakes paper 3 years ago. I started working on this. So, and we've only recently been able to sort of understand how to do this. And we are currently, Paul and Aaron, some others, we are working on making this truncation work. But then also, I think it's actually, at least in the context of if you include matter, so if you go to something like neutron stars, then the field redefinitions are not so obvious anymore, because it's not at all obvious whether they leave the physics invariant, because you also change the coupling to matter, right? So you make a very complicated theory where your new metric couples very differently to the matter, the neutron star, than the original one. And so even if you trust the perturbative field redefinitions, in the vacuum theory, the leading terms would then be of cubic order. But in the non-vacuum case, the leading terms would be those. So I think it's meaningful to make this one work and then to consider neutron stars. Otherwise, you can think of what I'm showing you now as a test bed for making this. All right.
So,
yeah.
I think all Figueras and collaborators, obviously not you included, work make simulations important. So
Yes,
part of the theory, yeah.
that's right. And they do that by a different way of making the equations well-posed. And in fact, it's actually, I think, in some sense, it's going to be related in the end to this, because what you're doing is you're capturing the new physics by an additional driver equation, which sort of you make sure that the equation has a certain structure such that the deviations are always driven back to the physical solution, or at least that's what they should do, and then you try to verify that they actually do that. And I think there's a way of thinking about these additional degrees of freedom. So they call it fixing of the equations. But there's a way of thinking of these additional degrees of freedom as the driver equations. So in some sense, it's a physical driver equation that we're using here. So we're sort of understanding the physics of the driver. And of course, you have now a covariant action, which you may or may not consider this. But yeah, you're right. There are some simulations, although, yeah, it's very hard to ensure that you actually capture the physics in this fixing approach. So I think it's definitely meaningful to have different simulations and try to compare different formulations. All right. Good. So then let me spend the rest on how to implement it or to actually get to physics. So I want to now talk about this quadratic theory. And as I mentioned, you can think of the result that I'm going to show in various different ways. I think the most sort of obvious and faithful way that the computer gives the results for is just that theory as a fundamental theory, right? By which I mean that I take the additional degrees of freedom, this one and this one, I take them to be physical. So that theory will have a ghost, and I will see whether the respective initial data results in a runaway or not. So that's certainly useful, but then you can also use it, as I mentioned, as a benchmark model to proceed to the higher order terms, or as the leading order corrections for field definitions or in non-vacuum simulations. I actually also think it's a super interesting question, which we can now answer even in the principle. In the gravitational case, at what point these field definitions break? Because there's a bunch of interesting papers in scalar tensor theories where you can perform field definitions, which are at least obviously invertible and fine. And you can really do crazy stuff. You can change even physical structures of the metric as of the space-time. And so I think at least some things are subtle. So I think it's going to be an interesting question. And then I mentioned this, that you can consider it as a fundamental theory. And there's some whole high energy story of why these terms are interesting, because they help you with quantizing. And in fact, while general relativity cannot be easily quantized, that theory you can quantize, subject to problems with the ghost. And there's a bunch of people which have ideas about the ghost, and I think this sort of understanding that if you make the ghosts heavy, they might decouple, can also be interesting again, the high energy story, but I'll not get into that. Okay, so what I want to do in this part is I want to convince you on the numerical side that at least from that layer, I don't only claim well-posedness by mathematical theorems, but I can actually perform numerically stable evolution. And then I want to look at isolated black holes, in particular on the stability of these black holes, which of course relates to the ghost question. And then on transitions to potentially other solutions of the theory. And then in the end, I'll talk a little bit about binary simulations, which we are currently performing. That's now work with a different collaborator who's at Los Alamos, Xid Lin. And there's already 2 papers and hopefully soon. Okay, so first numerical stability. So now if you perform numerical simulations, you are probably familiar with what I'm going to say. We use adaptive mesh refinement, obviously, because we really work in 3+1 dimensions. So that's crucial to making the numerics feasible. This particular code, which Hyun has actually developed, uses wavelet formulation and is very nicely scalable to a lot of cores. On the right here, you see a simulation. In this case, it's still GR. And we use 4th order finite differencing. That will be important on the next slide. And also 4th order evolution schemes in time. All right, the code is based on many people have contributed to the code. And Hyun is one of them that maintains it today. And of course, so in some sense, when I got into this whole project, I knew nothing about numerical relativity. That I know a little is thanks to it. It's thanks to Hyun. All right. So here's a robust stability test, whereby I mean that we take the Hamiltonian constraint with the corrections from the higher derivative terms. So there's still a Hamiltonian constraint. It just looks a little different than in GR. And of course, the Hamiltonian constraint should be preserved in time up to numerical noise in the simulation. And here we add additional noise to the initial data at some level in the simulation. And what you see is that as we reduce the original noise, we reduce sort of the noise even at long time in simulation. So what you expect is that if there is some problem with your numerics, then this degrades at late times. And in particular, if there's a numerical instability, it really would sort of blow up at some point. And at least for the simulation times that we performed, we don't observe. All right, then this is maybe even a little more interesting. Here you perform a so-called convergence test where you find order of your discretization scheme. So I said in the previous slide that we use fourth order finite differencing, and that's exactly the fourth order that we find here again. You just basically divide appropriately simulations with the respective resolution, and then I think this is a very good way of testing that the numerics is fine and that there's no instability, no numerical instability present. Notice that numerical instability is something different than physical instability. So it can still be that there's a physical instability. So it's numerically stable. And so now let's look at, started looking at isolated black holes. So there's a whole sort of separate story about linearized stability, and I think Valentin is one of the experts. You can take the field equations and you can linearize them, and you can really analytically, at least to some point, and then you have to solve a quasi-normal mode equation or a quasi-normal type equation for the respective frequencies. And then you can, by this almost analytical way, you can understand the linearized stability of the problem. Although a mathematician would object, and there's a whole more complicated way of understanding small perturbation stability, but at least for that's what mathematicians would call mode stability. But for a physicist, I think it's fine enough to say that if all these modes are stable, we expect the solution also to be stable. All right, so first of all, there's now multiple branches of black holes in that theory. So the theory is more complex than GR. Right, GR has only, so this is spherical symmetry. GR has only Schwarzschild black holes, which here I'm plotting the horizon size of the black hole and the asymptotic mass of the black hole, scaled by the mass of this additional M2 field. The scalar field you can completely forget for this question of black hole branches and stability. But the massive mode matters, and to be able to sort of represent everything in one plot, I have to rescale the quantities by M2. Now, this one is obviously Schwarzschild because its horizon radius equals 2m. And the other branch behaves very, very differently, meaning that if you increase the size of the black hole, its asymptotic mass drops, which is sort of exactly the opposite behavior than you have in the GR branch. And there's a particular point or a particular size of black holes where the two branches coincide. And we call that the crossing point. So all of what I'm telling you now has been known before. And even that has been known before. So you can now linearize the equations around the Schwarzschild branch. And then you can perform a stability analysis, which will reveal the imaginary part of the respective frequencies. And then if the imaginary part is positive, the respective frequency will grow in time, which signals an instability in that particular mode. So here you see that imaginary part as a function of the same axis in here. So as a function of the size of the black hole in appropriate units scaled by this M2. So this point is exactly this point. It's the branching point. And below the branch point, the Schwarzschild black hole is unstable. That result has been known before, and that I'm sure Vito has worked on. I think Richard was involved as well, right? You've recovered that instability in that paper, basically, which is basically valid for any spin-2 massive perturbation of the Schwarzschild black hole. And since this theory has a massive spin-2 field, we find exactly the same instability as well. Now, I'm calling this a Gregory-Laflamme instability because, funnily enough, it's exactly the same linearized perturbation equation than you get from taking a a string-like 5-dimensional object and compactifying 1 dimension. You also get a massive mode on the compactified direction, which causes the same linearized instability. So in that sense, the two problems, although one is 5-dimensional and one is 4-dimensional with higher derivatives, linearized, they are exactly the same, but only linearized. The nonlinear evolution will presumably proceed completely differently. All right, so that gives you not just an instability condition, but also a growth rate of the instability. And the growth rate is the highest somewhere in the middle of this interval. And on both sides of the highest point, the growth rate goes down. On one side, at some point, the instability is removed, and on the other side, it always remains, but it also becomes arbitrarily slow. Also, one word on the ghost. This instability is in the longest wavelength mode. And that's actually something that I think is also not really appreciated, that the ghost instability is not a high frequency instability. It occurs sort of at lowest frequencies, it's worse. It then moves stuff to higher frequencies. So it does cause typically a cascade to higher energy or to higher frequency. But the origin of the instability is not worse at higher frequency. It's worse at the lowest frequency. All right. So what generically holds, and actually that's the new part in this paper, we've done the same around the other branch, is that the small black holes are unstable in both branches. And so what we expect is that black holes can transition from this branch into this branch. And you see that. So before that, here are different simulations of a single black hole, with the red one being in this configuration and having the highest growth rates. And then the dotted lines, I guess, go down in this direction, and the dashed lines go down in this direction. And well, you can see exactly what I said before. And on both sides of the peak, the stability becomes lower. And actually, the two blue lines you cannot distinguish in the simulation time. They are here and there. But one of them should be stable, and the other one still has an instability. It's just a very, very long-lived instability. And that also makes the whole question of whether ghosts are stable or not very difficult, because at least numerically, because it's very hard, impossible to exclude long-term growth. All right. So now, yeah.
Can you make an entropy argument to justify this?
Yeah, so people have made entropy arguments to justify to claim that the instability should proceed and also should proceed instantaneously. I don't think these entropy arguments are rigorous, and I'm also very sure now that the instability does not proceed instantaneously, even in the continuum classical field theory. What is harder to understand is whether the instability can somehow be quenched, at least for a subset of initial data. That's something that I think is not clear at present. But for sure, it's not instantaneous. And in some sense, well-posedness excludes the possibility of instantaneous instability. And yeah. So people have made this argument that there's an infinite possibility of decay, right? There's an infinite phase space region which can decay. But I think the question is also whether that is accessible by a dynamical process, which the entropy argument doesn't talk about. That's a loophole.
So numerically, you can actually conceive a system that evolves into an unstable situation, in a stable configuration, and then proceeds to the final stable.
Well, I think the question is whether you would then have called the original system stable.
You would not, I guess.
So yeah, the difficulty is that I can be sure that the system does not lead to a runaway over some time by checking that my numerics are sufficiently converged, that they represent the continuum theory, that I think one can be convinced of. But whether it decays at some later time can only be achieved by an analytical proof. And so actually, like, if I get to the very last part, which I probably don't, then for point particles, there exist analytical counterexamples where you can rigorously prove that there's no runaway. And we are starting in Paris, which is the reason why I have the postdoc in Paris, to sort of understand the conditions of those arguments. All right, I think I'm starting to run out of time. So let me say that you can now transition even from one branch of the black hole, so from the Schwarzschild branch to the non-Schwarzschild branch. That works perfectly fine. And that again is an example of that the simulations actually, or the continuum field theory actually persists for some time in the evolution. And here you see these transitions, which is very nice is that the PI group around East has also started simulating these systems. So we have a very non-trivial check of the numerics because we haven't talked to them at all. They also use a reduction of an axisymmetric code in 2+1 dimensions, where we do the actual 3+1 simulation. And they use a harmonic gauge. We do not. We use a BSSN type formulation. So I think it's really a completely different setup. And we find by now the same physics, which is super nice. So we can observe these transitions. What we do not yet agree on, and I want to be open about it, is this other possibility. So they find that if they put perturbations at the other sign, then they can scale to sort of singular behavior. We have not yet observed that, and we don't really understand why, because at least the way that I understand our simulations is that we put random noise in the initial, which should at some times have one kinetic turn sign and the other. And so it should, if both of these behaviors occur in the full 3+1, then I think our simulations should show both branches. We don't see that. So that's something that remains to be done. But both simulations show that you can end up with transitions from one branch into the other branch. And that is what helps us with now performing the binary system simulations, because there's a whole different complication, which I haven't told you about, which is finding appropriate initial data. Because just as it's difficult to evolve these higher derivative equations, it's difficult to find appropriate initial data for the different black hole. Initial data is a difficult question, even at GR. Here we can get around that because the theory admits for GR solutions, which can be physically unstable and grow into the other solutions. So that's what we're making use of in the binary systems. And so, as I said, we are trying to perform now these binary simulations, are performing them. We have performed binary simulations in this regime that's also published, where the instability, the linearized instability is off. And we also find that there is no nonlinear instability. So there's nothing unstable about the ghost that regime. In fact, and that is related to the field redefinitions, I think, there's absolutely no deviations up to numerical noise from the binary merger. Then you can perform regime in this regime where you're sort of at the edge of the EFT, where you start to see the instability. That would be the branch point in the linearized plot that I showed. And then finally, currently, we're trying to go to that regime where you would really, I think, be away from the regime of validity of the EFT. And so you would simulate in the case where you take these degrees of freedom as being physical, right? If they excite a new solution, well, you've obviously taken them to be physical and you're not perturbatively close to the GR case anymore. But in principle, I don't expect by now that one cannot find situations where there's no runaway and one can even go through the full binary merger. So the reason why we haven't published those simulations is because there's difficulties with the apparent horizon finder if it gets far away from GR, and you still have to resolve. All right, so these simulations, as I said, here you see the trace of the orbit, and you see the comparison of general relativity, where we really just evolved general relativity, and quadratic gravity, where we also evolved these additional fields, fully nonlinear, as in formulation that I've shown before. And really, these two trajectories we can check up to numerical noise, they're the same. And I've shown this plot before, and I've gotten sort of, well, that's obvious and that's trivial because of the field redefinitions. But I think what this really means is that there's no nonlinear instability of the ghost. And I think that part is very non-trivial, that you can make a ghost heavy enough. And in this case, the heavy cutoff is just the linearized stability cutoff. And then it's fine. It also means that at least at the classical level, this quadratic gravity theory would be a perfect mimicker of vacuum GR, right? Even the whole nonlinear structure remains exactly the same. And in the second regime, we've performed simulations with these binary configurations, and we've gotten this first waveform, which I included in the first slide. We benchmark it against so-called Maya catalog, which is a different waveform catalog of GR simulations, and really find consistency at that level. And as I said, we're now sort of trying to perform simulations at the even smaller regime. So here, basically, we see here a simulation where the two binary black holes, they in-spiral, and while they in-spiral, they grow into the new solution, and then somehow the merger happens during that growth period. And of course, there's no physical argument of why the black hole should grow just in that moment of time. So what we want to achieve is we want to have a simulation where one black hole has fully transitioned, or both black holes have fully transitioned, and then the merger happens. That is in this regime where really the physics is very different. All right. And so we'll have to remain up to date for these simulations, hopefully this year, but maybe not. And then I think this is really nice because it gives us a way to sort of perform field redefinition, perform numerical relativity for really a whole class of fields, if we can deal with the ghost. And with that, thanks.
Well, we're a bit over time, but if anyone has one or two quick questions.
So you said in some cases you have problems with your horizon finder. There is theories, but I wonder why that should be the case.
In principle, that should not. I think it's a technical issue. Right? It shouldn't be the case. It's just that the horizon finder, so if it's really far away from GR, there can really be dumb code issues in a sense that the code behaves, some fields run over value and stuff like that. So it's not, I don't think it's a fundamental issue. I hope we'll resolve it soon. I don't really know where it comes from at this point. But so it's the horizon finder, which seems to be tricky, and the wave extraction at infinity, which seems to be tricky. Where with the wave extraction, I'm a little less sure that it cannot be physics because you have additional fields. But still, I think at least close to GR, it should be a problem if the solution remains asymptotically flat. So yeah.
I have a question. Probably you mentioned it and I didn't quite understand, but so there are some exact partial solutions that are unstable in this theory, right?
So there's some extra?
No, exact partial solutions
Yes.
that are unstable, right?
Yes.
So I wonder how is it that you are still perturbatively close to GR if you start with exact, GR initial data that you would expect in that case to be stable, and then you depart from it.
Yeah, I think
drastically.
you're not. So I think so. So as I said before, in the regime where you have GR black holes and they are stable, you're obviously everywhere in the future evolution, you will remain with the GR black hole and remain stable. So the full, entire future time evolution will be perturbatively close to GR. For the case where you have an instability, or a soft instability or a slow instability, in the beginning, you will be perturbatively close to GR. But then, of course, the instability will take you away from being close to GR. And as soon as it does that, this part of the manifold will no longer be perturbatively close to GR. And so it's not surprising that this part you cannot remove by field definitions.
Well, okay, but this leads me to another thing that, seems puzzling to me in your theory is that when you do this order reduction to get second order equations, right, you would have like reduction constraints, like Ricci being derivatives of the metric, right? And you're involving both. Those constraints wouldn't propagate with the equations of motion, right? Like, how can you guarantee that you start with initial data, then in the evolution, the second order system resembles the fourth order?
No, that is part of proving well-posedness. You have to also show that the constraints propagate
Yes,
in the
that's what I
proper
thought.
way. Exactly, and I haven't shown you that in the detail, but we do that.
But that does happen. Okay. So just unstable.
So yes, the constraints need to propagate as, I mean, they need to be preserved in the
That was why the other example tricked me. Okay.
If you enjoyed the video, like and subscribe.